Hi everybody, this is Mr. Valley, and welcome to our last podcast of Unit 6. We had 5 of them in here, so it's kind of a lot. We're going to go over the basics of fission, fusion, use of radioactivity, and our one little calculation of half-life. So let's hop right into it. Okay, first of all, nuclear fission. Remember, fission means splitting. So the way these things split is you basically have a little gun that shoots neutrons at something. Okay, so you shoot a little neutron. So you can see here, this, I don't know how well this turns out, this is a little neutron that's being shot at a giant nucleus, and it splits into 2 smaller nuclei, and then you get a few more neutrons. You always get more than 1 neutron, so you get 2, 3, 4 neutrons, and then energy. So splitting a neutron gets energy, so that would be one of the ways we do it. So here we have uranium plus a neutron, splits into 2 smaller ones, and then you get 3 neutrons plus energy. In a different case, you can get different atoms, different number of neutrons, plus you'll always get energy. So in fission, one of the products is always energy and neutrons. So what are always the products of nuclear fission? Smaller nuclei, neutrons, and energy. So I should write that down. Smaller nuclei, that's the plural of nucleus, neutrons, and energy. What's interesting about this is if you're shooting neutrons, and that's what causes the reaction because you're shooting a neutron, is you can get a chain reaction. A reaction in which the product of one step is the reactant in another step. So in this case, neutrons. So if one of my products, if my products are always nuclei, so I've got X plus neutron, yields nuclei plus neutron plus energy, and usually it's 2 or 3 or 4 neutrons. That means I can now do twice the amount. So we think of chain reactions going out of control, and each time it will double or triple, typically, to go through it. These things start with a critical mass, the smallest amount of fissionable materials necessary to support a continuing chain reaction. So you need a certain density for the reaction to take place, or these neutrons will not hit other nuclei and you won't get your reaction to take place. So you want to be able to control this in a power plant, and so a power plant wants to control this, and a bomb doesn't necessarily want to control it as much as be able to predict how big the boom's going to be. Okay. In a power plant, they actually have what's called control rods that they stick in there to absorb neutrons. So in the nuclear reaction, they'll actually put in rods that will absorb neutrons to reduce the rate of the reaction so the reactor doesn't produce too much energy. If you produce too much energy, you're going to overheat, which would be very bad. But there are tons of safety precautions put in there so that it is. Fusion reactions. Fusion is a combination of light nuclei. So here we're using lighter nuclei to form heavier nuclei. A major fusion reaction occurs continuously in the sun and other stars, pretty much not other places. The reason why is, I think that's the next part that goes through it. So we're going to have small things. So we have hydrogens combining to make heliums, and in this case beta particles and things like that. The reason why fission is easy but fusion is tough is if you shoot a neutron at a nucleus, there's no repulsion. A neutron's charge is 0. A nucleus charge is positive because neutrons are 0 and protons are positive. But if I shoot a positive nucleus, this would be fusion. If I shoot a positive nucleus at another positive nucleus, they repel each other, so it takes a lot more energy to overcome that repulsion. The other thing, if we're trying to calculate how much energy there is, if you add the mass of protons and neutrons, you get less than the mass of the nucleus. So if we're just looking at the nucleus, of course electrons have mass, but they're not really involved in this. Some mass is converted to energy to hold the repulsive protons together. I call the neutrons the glue that holds it together. The real glue that holds it together is also the binding energy. So some of this mass that used to exist is changed into energy to hold it together, and that's called the mass defect. And when you look at nuclear reactions, the energy you get is the mass, which normally we think of mass as being in grams, but it's kilograms, times the speed of light, which is 3 times 10 to the 8th squared. So that's not squared, squared. So we're talking about 10 to the 16th, which is a big number, of energy that comes through destroying, not destroying, but converting just a little bit of mass. So that's why nuclear power things have so much energy. You're multiplying it times the speed of light squared. Nuclear things have other uses besides power plants and bombs, and one of them would be medical. They actually use plutonium-238 to power pacemakers. A pacemaker is in your heart, and basically what it does is it causes an electrical impulse that makes your heart beat at a regular pace. So it's a pacemaker. It makes your heart beats. It's got the pace that it needs. It makes the pace that it needs. And it needs a battery that will run a long, 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 long time, because if the battery dies, the patient's heart beats irregularly, at least until they die. So pacemakers are a great invention, but they need a good power source, and plutonium-238 is used to power the pacemakers. Again, think of the issues you'd have. Oh my gosh, you're putting radioactive things in your body. Oh no, how terrible. But again, it must be safe. I mean, I would think it's going to be safe for 10 to 15 years, because most people that get pacemakers get them in, I don't know, say your 60s, and people don't live forever, sadly. All right, medical tracers. The other thing that you can do is you can radioactively put a marker onto a drug. So you can have this little pill, and you can put this radioactive marker on it. Whee! And say you're trying to figure out something in the digestive system. So you've got a person here who's going to eat, like Pac-Man, who's going to eat these things. And then this radioactive tracer, boy, they have a funny looking shape of their body. And then this tracer, I should make it a color, it's easier to see. After they eat it, the tracer might go to different places. So the tracer might not go to the liver, and it should. Most drugs should go to your liver to be detoxified and go through it. And if it never goes to your liver, you can go, oh, bad liver. So if drugs that you're trying to eliminate never go to your liver, you can go, oh, bad liver. Or if these things go into your brain, and then you're tracing them to try and see parts of your brain, and it only goes to part of your brain but not your whole brain, then you start to realize there's problems. So another type of tracer type thing you can go through here. A PET scan detects abnormalities in living tissue without disrupting the tissue. So you can use some of these tracer things to figure out what it is. This is a fully active brain. See those lights? You can see all the things that are going on. The blues are very strong. You see the oranges and reds or greens, or I don't even know what color it is. This brain is missing some things. So this would be normal, and this would be abnormal. Okay? So you should be able to see some of the uses of that. There's some new cancer treatment things that are going on too. Cancer cells are uncontrolled growth. Cancer cells need extra nutrients, and really they have exposed DNA. I don't expect you to remember too much about biology, but you should know that DNA is wound up in a double helix. And hopefully you remember when cells divide, the double helix unwinds for replication. Now once that's unwound, that happens during growth, once that is unwound, those DNA nucleotides are very susceptible to radioactivity. So if you cause mutations, remember most mutations are bad, so that means it will probably kill the cell. If you're killing cancer cells, that's good. However, all cells divide at least a little bit. So the idea here is you're sending radioactive nutrients that destroy the DNA. Now, the DNA you want to destroy are the growing DNA. And since cancer cells are growing uncontrollably, they're going to die first. So the goal is to kill the cancer before you kill the patient. And it's weird to think of it that way, but that's exactly what they're trying to do, is kill the cancer for the patient. Engineering thickness control. If I have a plate and I have a radioactive sample, it'll be shooting up its little beams through here. If it's a thin plate, maybe 2/3 of the beams will go through. If I have a sample and it shoots up the same thing, and I have a thicker plate, maybe only one beam will come through. And that way you can, using an equation, figure out the thickness of it. The exact same thing is true for leak detection. If instead of this being just a sample that's here, if you make it a pipe, and this is a wall you don't want to break. So let's pretend that they found out that there's a leaky pipe behind some valuable fresco in Italy. They don't want to take out the whole thing. They want to minimize the damage they're going to cause, so they want to do it in as few places as possible by putting something radioactive into the pipe. That means as it goes through here, once it gets to this leak, the place with the highest radiation would be where the leak is, so then you can minimize the damage you do through those things. Of course, we have power generation, and booming would be bombs. Archaeological. Living things have the same ratio of carbon-14 as the atmosphere. Dead things lose their carbon-14 in a half-life manner. You did half-life in biology, but I'm sure you forgot it. Half-life. Atoms decay, but not at a constant rate. A constant rate would be you lose 10 an hour. And that doesn't happen. Half of the atoms decay every time period. That time period is called a half-life. So this is basically an exercise in times in and divides in. On this graph, what I have is a ratio of 100%. This number right here is 50. The time it takes to get to 50 is what we've called T 1/2. My line is just a curve. Whee! So half of 50 would be 25. Notice the time increment is exactly the same. This would be 2 half-lives. Half of 25 would be 12.5. And that would be the same time increment. Half of that would be 6.125, half of that, and you can tell just by going on and on and on with it. So ours will be very simple. We'll be using whole half-lives or whole halves of things to go through it. So let's just do a couple of examples. An isotope of radon has a half-life of 36 minutes. What fraction of the original quantity of actinium after 300, this should be radon remains after 360 minutes. So after 360 minutes, that's 10 half-lives, right? That's not a big jump in math, is it? Every 36 minutes, that's 10 half-lives. So what I'm going to do is just cut it in half 10 times. Okay, what fraction of the original quantity? My original fraction is 1, right? Then I'm going to do a half, a quarter. So this is your first half-life. Second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. 1/1024th would be left, right? That's all you have to do. 1,080 minutes. So what I'm going to do is I'm going to take 1,080. Get out my handy dandy little calculator here. Oh, mine's only solar. I've got issues now. 1,080. Let's see if I can find a non-solar calculator. I'm sitting in the dark. 1080 divided by 36 would be 30 half-lives. So then what I can do to make it a little bit quicker is I can take 1 divided by 2 to the 30th. If you notice, this right here is taking 1 divided by 2 to the 10th. Okay? So, yep. So I'm going to do 1 divided by quantity 2 raised to the 30th quantity. I probably didn't need the quantity, but that's it. And I'm going to have, what fraction? It's going to be 9.31 e to the negative 10 would be the fraction of it. Okay? And that's it. Check the next one. The half-life of carbon-14 is 5580 years. A 5-gram sample of carbon prepared from a newly cut lumber gave a count rate of 2.02 counts per second. So this would be the Geiger counter. Remember, click, 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 so you get 2.02 clicks per second. 5-gram sample of carbon from a relic. By the way, a relic is either a piece of a dead dude, or person, girl, or something that they wore or found valuable. I know all Catholic churches have a relic in their altar, so they either have a piece of a dead saint or something that is precious to them, perhaps a cloth, a burial cloth or something like that, or some book that they wrote. This is 1.81 counts per second. Calculate the age of the relic. This is one that I forgot I didn't use the right equation for. Yay! Calculate the age of the relic. We can't. We have to use the more advanced equation that I thought I had and that we no longer do at this level. So, sorry. Yeah, this would have to be something that would be 1.01, which I'm sure is what I thought it was. So 1.01 accounts per second. Calculate the age of the relic, and the relic would be 1.01 would be exactly half of it, right? So that would be 5580. But we get to skip this one and be glad. Get out a little bit quicker. For 26 days, a radioactive material is found to have a 1/16th of its original activity. What is the half-life of the radioactive isotope present in the material? So what I'm going to do here is I know it's going to go 1, 1/2, 1/8, 1/16th. That means it took 1, 2, 3 half-lives, right? So 26 days was 3 half-lives. So 26 over 3 would be 8.67 days. Review. Fission is splitting, fusion is sticking, or that's good enough. Radioactivity has many specific uses to know, and half-life calculations are fun. So that is it. Enjoy your evening, and look forward to the pod quiz tomorrow. I know I am.